In this video, we are going to prove this theorem that for every positive real number x and every positive integer n, there exists a unique positive real number y such that y raised to n is equals to x. Uh, we will begin this proof by assuming existence of such a real number y, and we'll first prove uniqueness. Once uniqueness is done, we will then prove existence. This is because proving uniqueness is straightforward. So to prove uniqueness, we will employ a method of contradiction. So let us assume there exist y1 and y2 such that y1 raised to n equals to x and y2 raised to n equals to x. And we are assuming that y1 is not equals to y2. So without loss of generality, we can assume that y1 is less than y2. And this would imply that y1 raised to n is less than y2 raised to n. We are assuming that y1 and y2 are positive because we are assuming existence of a positive real y such that y raised to n equals to x. And since y1 raised to n is x, y2 raised to n is also x, so we get x is less than x, which is a contradiction. So this shows that if there exists a positive real number y such that y raised to n equals to x, then the number is going to be unique. Regarding existence of such a y, we consider a subset of R defined as collection of all real numbers such that t is positive and t raised to n is strictly less than x. So we will claim that this set is non-empty. This is bounded above. So it is going to admit a supremum, and we are going to show that the supremum is the number y which we are trying to find out. So we will show the following things. First is E is non-empty. E is bounded above. Once these two properties are there, by completeness axiom, supremum of E is going to be a real number, and we will assume that y equals to supremum of E. And then we are going to show that this y satisfies the equation, that means y raised to n is equals to x. Now to show y raised to n equals to x, we will divide this into two cases. We will show that y raised to n cannot be bigger than x. So we'll assume y raised to n is bigger than x and arrive at a contradiction. And we'll also show that y raised to n cannot be less than x. So we'll assume that y raised to n is less than x and then arrive at a contradiction. So we will divide this proof into three steps. In step 1, we are going to show that E is non-empty. This should be not equals to. E is non-empty and bounded above. In second step, we are going to show that y raised to n equals to x by dividing it into two parts. Okay, so we begin by showing that E is non-empty. This is what we want to show. To show this, we need to find an element T which belongs to E. To find this element, what we will do is we will find a number T such that T is less than x and T raised to n is less than equals to T. So we'll find a T such that T is less than x and T raised to n is less than equals to T, because this will imply that since T raised to n is less than equals to T and T is strictly less than x, this will show that T raised to n is less than x, and that would imply that T is in E. Because E was collection of all positive numbers for which T raised to n was strictly less than x, and that's what we would have shown here if we can show this. Now we want to construct a positive number with this property. So our t should be less than 1. So we will show that t equals to x divided by x plus 1 is going to satisfy our requirements. So we will show that this element is going to belong to E. So since x is positive, we see that t is greater than 0, and we also see that t is less than 1 because x plus 1 is always bigger than x. Since t is less than 1, this will imply that t raised to n is always going to be smaller than t. And we can also see that t is also less than x because x is always less than x plus x square. X square is non-negative, in fact it is positive. So this implies that x divided by x plus 1 will be less than x. So t is also less than x. So this means we are through. We have shown that t raised to n is strictly less than x. This implies t belongs to E. So E is non-empty. Next we claim that E is bounded above. So we need to find an upper bound on E. So to prove this, we are going to show the following. So we will find U. We will find some real number U such that whenever t is bigger than U, this will imply that t raised to n is bigger than equals to x. So this is what we will show. Now if you just look at the contrapositive of this statement, that is going to be t raised to n less than x implies t is less than equals to u. T raised to n is less than x, this implies t belongs to E, and this gives you that t is less than equals to u, which is same as saying that E is bounded above. And upper bound is going to be u. So showing this is enough to show that our set E is bounded above. Now to find this number u, we will find u such that u is bigger than x and u raised to n is bigger than equals to u. Because if we can find u satisfying these two conditions, then t raised to n, or rather, since this is what we want to show, so whenever t is bigger than u, this will imply that t raised to n is bigger than u raised to n. U raised to n is bigger than u because that is what that is something that we want in our construction, and u is bigger than x. So this implies so if we can find u satisfying these set of conditions, then we will be able to show this implication, which is equivalent to saying that E is bounded. So this was the idea, and now we write it precisely. So we assume that u is x plus 1, and we are going to show that this value of u is the value that we want, is actually one of the value that we want. So we assume that t is bigger than u, and we want to show that t raised to n is bigger than equals to x. So whenever t is bigger than u, t raised to n will be bigger than equals to t, because t is bigger than u is x plus 1, x plus 1 is bigger than 1. So if t is bigger than 1, then t raised to n is bigger than equals to t. So this further tells us that t is bigger than u, and u is bigger than x, right? Because u is x plus 1, which is bigger than x. So t raised to n is bigger than equals to x, and this implies that t does not belong to E. t was set of all positive real numbers such that t raised to n is less than x. And since here, whenever t is bigger than u, t raised to n is bigger than x. So that means t does not belong to E. Again, if we just write contrapositive of this, so negation of this is going to be if t belongs to E, then negation of this t is less than equals to u. So if t belongs to E, then u is an upper bound. So this completes the proof that E is bounded above. We have already shown that E is non-empty. So by completeness axiom, supremum of E is going to be a real number, and we are assuming that that particular real number is being denoted by Y. Next, our claim is that this Y is going to satisfy the equation y raised to n equals to x. So as I said earlier, we will divide this proof into two parts. Let us take part 1 where y raised to n is less than x. And first I'll explain the idea behind the proof, and then I'll let on the precise proof. In this assumption, we are looking for a contradiction of the type that y is not an upper bound of E. Because y is supremum of E, and here we have inequality that y raised to n is smaller than x. So we are looking for a contradiction which is of the form that y is not an upper bound of E, because supremum is supposed to be the least upper bound. So if y raised to n is less than x, then we must have something like that y is not an upper bound of E. Now, what we mean by y is not an upper bound of E, that means we want some element of E such that t is bigger than y. If y is an upper bound, then t is less than equals to y for every t in E. If it is not an upper bound, so we want t in E such that t is bigger than y. Now, to prove this, we first of all we want t belonging to E. That means t raised to n should be less than x. Then we want t to be bigger than y, so we'll assume t to be of the form y plus h for some suitable h. So we will choose our h so that our requirement is satisfied. So we will choose h bigger than 0. First of all, t should be element of E, that means t raised to n should be x. So t raised to n is y plus h raised to n. This should be less than x. Only then t will belong to E. And then for further proof, we will require an inequality. So it is a simple inequality which can be obtained by basic multiplication or division. So for any numbers a and b, we can assume a and b to be positive. So if a and b are positive, you can show that b raised to n minus a raised to n can be written in this form. Now, in this identity, when we have this condition that a is less than b, then b raised to n minus a raised to n will be less than. I'll keep this term as it is, b minus a. Now I'm going to use the property that a is less than b. So first term is as it is. In second term, I'm using inequality a is less than b, so it again becomes b raised to n minus 1. So in all the terms, I'm going to use the inequality that a is less than b. So everywhere I'm going to get b raised to n minus 1. There are total n terms, so this becomes n b raised to n minus 1 multiplied by b minus a. So I'm going to call this inequality star. This will be used in both the parts where y raised to n is less than x as well as y raised to n is now bigger than x. Now apply this inequality for some particular choice of a and b. So choose a equals to y and b equals to y plus h. Then we see that our hypothesis is satisfied, that a and b both are positive, and a is less than b. So if we apply this inequality with these choices of a and b, we will get y plus h raised to n minus y raised to n is smaller than n times b is y plus h raised to n minus 1 multiplied by b minus a, so y plus h minus y. So this will be nh y plus h raised to n minus 1. Now we are trying to show that there exists some h positive such that y plus h raised to n is less than x. So we will be through if we can show that. So we will show that nh y plus h raised to n minus 1, this is smaller than x minus y raised to n. Because if we can show this, then y plus h raised to n minus y raised to n will be less than x minus y raised to n. That is equivalent to y plus h raised to n is smaller than x. So this is what we are going to show. Now to show this, our job will be simple if we assume that h is less than 1. So since we are looking for finding out a value of h, so we can put as many restrictions on h as we want, as long as it gives us a positive real number satisfying our requirements. So if h is less than 1, then nh, this will be smaller than n. I'm keeping this h as it is. Y plus h will be smaller than y plus 1. Because h is less than 1, so y plus h will be less than y plus 1. Now it is easy for me to make this quantity smaller than x minus y raised to n. So from here I'll get h to be smaller than x minus y raised to n divided by n times. So if I had tried to solve this inequality and from there try to get a value of h, I don't know even if that is possible. If it is possible, it is going to be extremely difficult. But if we make this simple assumption that h is less than 1, use it here, and from here it is easy for us to get a value of h. Also observe that our hypothesis was y raised to n is less than x, and since y raised to n is less than x, this quantity x minus y raised to n is positive. So this right hand side of this inequality is going to give you a positive number. Okay, so let us look at what conditions we put on h for showing this inequality. The conditions were that h should be less than 1 and h should be less than this quantity. So the h we actually require has to satisfy both inequalities, so we can choose h to be minimum of these two quantities. So if we choose h to be minimum of these quantities, we will be through. Our y plus h will satisfy the required conditions. So this was the idea behind the proof. Now let us write down the precise proof. So this is proof of part 1. I had divided into two parts, y raised to n less than x and bigger than x. So this is formal proof of part 1. So here we assume that y raised to n is less than x, and we are choosing h to be minimum of 1 comma x minus y raised to n divided by n y plus 1 raised to n minus 1. So if we make this choice of h, then we have seen this calculation that y plus h raised to n minus y raised to n. When we applied that inequality, this was less than nh times y plus h raised to n minus 1. Since h is less than 1, so h is also less than x minus y raised to n divided by n y plus 1 raised to n minus 1. So this is equals to x minus y raised to n, and that implies this implies y plus h belongs to E. Recall, y was the supremum of E. Supremum is an upper bound. That means no number bigger than that can be element of E. Here y plus h is bigger than y. It is also an element of E. This implies y is not an upper bound of E. Because if y is an upper bound, then t has to be less than equals to y for every t in E. And here you have found out an element of E which is bigger than, sorry, this should be y, not h. Here we have found out an element of E which is bigger than y, so y cannot be an upper bound. So this is a contradiction. Thus, our hypothesis was that y raised to n is less than x. So this cannot be true. And what this means is y raised to n has to be bigger than or equals to x. So this will take us to part 2 of the proof. In part 2, we will assume that y raised to n is bigger than x, and then we will arrive at a contradiction. So idea in this proof is again similar to part 1. Since y was supremum and we are assuming the inequality y raised to n bigger than x, so here we are looking for a contradiction which is of the type. So we want a contradiction of the type where a number that is smaller than y is an upper bound of E. So since y is supremum, that is least upper bound, and we have y raised to n bigger than x, so there should exist some number which is smaller than y, with still an upper bound, and that will again contradict the fact that y is supremum. Supremum is the smallest upper bound, so anything is smaller than y cannot be an upper bound of E. Okay, so for this, this is what we will show. So we will show that whenever t is bigger than y minus k for some k positive, this would imply that okay, so in the previous part we were looking for a number bigger than y, so we assumed it of the form y plus h. We found our h out. Here we are looking for a number smaller than y, so we are looking for a number of the form y minus k. We'll choose this k suitably. Now, if we simply look at contrapositive of this statement, that would be a negation of this, which means t raised to n is strictly less than x. That implies negation of this. that is going to be t less than equals to y minus k. T raised to n is less than x, so that means t belongs to E. That was the definition of E. And this implies that y minus k is an upper bound of E. And that is what we want. We want a number smaller than y, that is y minus k here, and that is an upper bound of E. So it is enough for us to show that this implication is true. So that is what we are going to do. Okay, so we have to choose k so that this implication is true. So we want t bigger than y minus k. Uh, this will imply that t raised to n is bigger than y minus k raised to n. If you multiply both sides by minus, so minus t raised to n will be less than, well, add y raised to n both sides, so we'll get y raised to n minus t raised to n less than y raised to n minus y minus k raised to n. Now we will apply inequality star. So if you recall, we had proved that if 0 less than a less than b, then this implies b raised to n minus a raised to n is less than n times. So we are going to apply this inequality on the right hand side. So let us choose b equals to y, a equals to y minus k. So this will give us b raised to n, that is y raised to n minus y minus k raised to n, smaller than n times b raised to n minus 1, b minus a, sorry, there is no n. This was the inequality. So this becomes n times k times y raised to n minus 1. So from here we get y raised to n minus t raised to n is strictly less than n times k times y raised to n minus 1. So if we choose k equals to y raised to n minus x divided by ny raised to n minus 1, then this will be strictly smaller than y raised to n minus x, and that will give me this, and that is precisely what we wanted. So we started with t bigger than y minus k, and if we choose k to be this, then t has to be bigger than equals to x, and that was our aim. So this was the idea behind this proof. We can observe one more thing, that we are finding a number of the form y minus k. We also want this to be positive. We want to show that y minus k is an upper bound of E, so we want this to be positive. And we can see that this is actually true because k is because our hypothesis in this part was y raised to n is bigger than x. So this is actually first of all k is actually positive, and then if we look at y minus k, for that again if we start with the so if we start with the definition of k, this will be strictly less than y raised to n divided by which is y divided by n, and that is less than equals to y. So this implies y minus k is greater than 0. So both k and y minus k both are positive numbers. Okay, so let us write the formal proof of part 2 by combining all these ideas. So in this part we assume that y raised to n is bigger than x, and then we choose k to be equals to y raised to n minus x divided by ny raised to n minus 1, then we see that 0 is less than k less than y, so that y minus k is positive. And we shown that whenever t is bigger than y minus k, this implies y raised to n minus t raised to n minus y minus k raised to n. This we showed to be less than equals to nk times y raised to n minus 1. On substituting value of k, this value of k, this is same as y raised to n minus x. So this implies raised to n is less than minus x. That implies t raised to n is this is just x. T raised to n is bigger than equals to x. And if t raised to n is bigger than sorry, strictly bigger than x. If t raised to n is strictly bigger than x, that means t does not belong to E. So we have shown that if t is bigger than y minus k, then t does not belong to E. Its contrapositive will be if t belongs to E, then t has to be less than equals to y minus k. So this shows that we have a number which is smaller than y, and it is also an upper bound. So this contradicts that y equals to supremum of E, and by supremum we mean it contradicts that supremum is the least upper bound. So this completes proof of this theorem.